Today we will study Cauchy's theorem. Cauchy's theorem. Cauchy's theorem for finite groups. For finite groups. लास्ट टाइम हमने बात की थी फाइनाइट एबिलियन ग्रुप्स की। इस बार हम लोग सिर्फ फाइनाइट ग्रुप्स की बात करेंगे। इसकी जो स्टेटमेंट रहती है, स्टेटमेंट वो क्या है, स्टेटमेंट की बात करते हैं जरा। स्टेटमेंट रहती है कि लेट जी बी ए फाइनाइट ग्रुप एंड पी बी ए प्राइम नंबर, बी प्राइम if P divides order of G, then G as an element of order P. So what is the meaning of the statement? This statement states that एनालिसिस करते हैं इसका। एनालिसिस क्या है? एनालिसिस इसका रहता है जी, if G is finite abelian group. So we are taking here only finite abelian group, sorry, finite group, not abelian group, only a finite group. जो पहले हमने थ्योरम की थी दैट वाज फॉर abelian group, finite abelian group. Now we are doing this theorem for finite group only. The case is same. If P divides order of G, then there exists A belongs to G such that order of A is equal to P. This is what we have to prove. So proof is very much similar to the previous one. So let's do it. Proof. Now it is given that given order of G, given G is finite. G is finite group. So let order of G is equal to n. अगर finite है तो इसका कोई order होगा. Let the order of G is equal to n. Now the possibilities. Now there are two possibilities. There are two possibilities. Abilities. Either n is equal to 1 or n is greater than 1. So let us take the case. If n is equal to 1, then there does not exist any prime. कोई भी prime ऐसा नहीं है. Prime P such that P divides 1. There is no prime which divides 1. So therefore, there is no question of existence of element of order P. Order P. Okay. So this is for n. So therefore, this case is not possible. So only possibility is therefore n is greater than 1. So we are taking, so order of G is equal to n greater than 1. Now, now we will prove, now we will prove this theorem through the method of mathematical induction. मैथमेटिकल इंडक्शन का मतलब क्या है? n इज इक्वल टू 2 के लिए प्रूव करेंगे, फिर n लेस देन Suppose suppose the result hold for all finite groups less than n of order less than n. Then we will prove for n also. So this is what we are going to do. So what step by step we will do this. Suppose the result is true for let me check. We have to prove the result for. First we will prove. First we will prove the result for n is equal to 2. So when n is equal to 2, that is order of G is equal to 2. Now P divides order of G. This implies that P divides 2. This implies that P is equal to 2. So we need an element of order 2. So we need an element of order 2. Now order of G is equal to 2, which is prime. So every prime order group is cyclic. This implies that G is cyclic. If G is cyclic, this means that there exists an element belongs to G which generates G, which is generator of G, and order of G is equal to order of A is equal to P, or that is 2 and is equal to P. So we are getting an element of order 2. So this, therefore, for order of G is equal to 2, there exists P is equal to 2, uh, P is equal to 2 dividing order of G. There exists implies there exists an element of order 2. That is, there exists A belongs to G, so that order of A is equal to 2. So thus the result holds for n is equal to 2. Therefore, the result is true for n is equal to 2. So take the induction hypothesis. Induction hypothesis. Suppose the result is true for all finite groups of order less than n. So all the finite groups which are less than n, the result holds. That is for all finite groups of order n, there exists an element A belongs to G, so that order of A is equal to P. This is what we are getting when the order of the group is less than n. Now we will prove, not to complete the hypothesis. Now, to complete the induction hypothesis, we have to show that the result is true for all n. So we are going to check the result for n also. Now, so So what happens? Now, what happens? Order of G is equal to n. Now, order of G is equal to n. Now we will check whether for order of G is equal to n, this result holds or not. So there are two cases. There are two cases. Two cases. Either G as a proper subgroup, or G as no proper subgroup. No proper subgroup. These are the two cases we are getting. So we are taking order of this is equal to n, and there are two cases arises. That two cases are either G as a proper subgroup or G as no proper subgroup. Now, if G as a proper subgroup, then what happens? Sorry, subcase, subcase one. Sorry, case one, not subcase. This case one. When we will take first as no proper subgroup. When G as no proper subgroup. It is not having any proper subgroup, and and n is greater than 1. This means that either the only subgroup the only subgroup of G is G. Now, P divides order of G. This means that order of G is prime. Now, any group of prime order is a cyclic group, right? Any prime order group is a prime order. This means that G is a prime order group. This means what? G is cyclic. G is cyclic. Obviously, G is cyclic. This means that it has a generator. So there exists A belongs to G, so that G is generated by an element, and we know that for a cyclic group, order of G and order of generator is same. So we are getting an element A which has the order P. So this is what we have to prove. So for this case, for case one, when it is having a no proper subgroup, so this is we are getting. So therefore, there exists A belongs to G, so that order of A is equal to P. So we are getting an element whose order is P. Now the second case is case second. Case second. This is the case when G as a proper subgroup. Proper subgroup. Right? This is what we are getting. Second case. For second case, we will see what happens when G is a proper subgroup. Now let करते हैं. So let करते हैं. Let H be a proper subgroup of G. It is a proper subgroup. This means that H is not equal to G. So this is a proper subgroup, no? So this means that order of H is strictly less than order of G. This is what we are getting. Now there are two possibilities again. Two possibilities. Again, there are two possibilities. Two possibilities. that is this P divides order of H, or P divides with does not divides order of H. These are the two possibilities we are getting, because P are already dividing the order of G. So there is a possibility that P divides order of H, or P does not divides order of H. So we are getting two subcases. Subcase 1. Subcase 1. When P divides order of H. When P divides order of H, then what happens? Now P divides order of H. Also, H is a proper subgroup of G. This means that order of H is less than order of G, and this is equal to N. So we are getting P divides order of H, and order of H is less than N. So by induction hypothesis. So we have induction hypothesis. Let us see. Induction hypothesis says that if we are having a group, so if we are a group of order less than N, if we are getting a group of order less than N, and P divides order of G, then we are getting a an element of order P. So we are using this statement. Now we are getting P divides order of H, and order of H is less than N. This means that by induction induction hypothesis there exists an element A belongs to H, say that order of A is equal to P. Now, since H is a subset of G, this means that this statement is true for G also. There exists an element G, A belongs to G, say that order of A is equal to P. So we have proved that there exists an element. So therefore, there exists an element A belongs to G, say that order of A is equal to P. So the result is true when the subcase 1, when P divides order of H. So the result is true. Now we will see the result subcase second. We will see the result for case when P does not divides order of H. When P is not dividing the order of H. Now, because this is not an abelian group, so in this case, we are going to use the class equation. So we are taking P does not divide the order of H for all proper, because this is a proper subgroup H of G. Any proper subgroup, this is holding that P does not divide the order of H. Now, by class equation, we know that we are using the class equation to prove this. By class equation, what we have order of G is equal to order of ZG plus summation A don't belongs to ZG. These are not the elements of ZG. Order of G divided by order of N of A. Now we will work on this. Let it be equation 1. Now, now we know A belongs to Z implies that order of, if and only if, order of G is equal to order of NA. This is the result. So this implies that if A don't belongs to Z, this implies that uh, order of G, we can say like this, order of N of A is not equal to order of G. Now, NA is a subgroup of, now NA is a subgroup of G. अगर Na जो है दिस इज सब ग्रुप ऑफ G और इसका ऑर्डर इसके बराबर नहीं है, तो इसका मतलब क्या हो गया? ऑर्डर ऑफ N ऑफ A is less than order of G. This is what we are getting. Fine. So this is what we are getting. Now, now what is this is Na is what? Now Na is a subgroup of is a subgroup, actually proper subgroup, is a proper subgroup of G. If Na is a proper subgroup of G, this means that P does not divides order of N of A, because we have taken the case, because this is a case where P, if P does not divides order of H for all subgroup, for all proper subgroups, कोई भी subgroup proper subgroup होगा उसके order को ये divide ही नहीं करेगा, तो Na भी तो proper subgroup है, इसका मतलब P is not dividing the order of G. Now if this is not dividing the order of G, now we can see that, now we can say, now order of G can be written as order of G by order of N of A. This can be written as order of N of A. Fine. So this can be further written as order of G by order of N. Sorry, let me write it collectively. Order of G mod N of A. इसका order हो जाएगा. And this is equal to order of N of A. Now, we have written here P does not divide the order of. Now P divides, this is given that P divides order of G. This is given. This means P divides order of G by NA and order of N of A. Fine. If this but P don't divides order of Na, this means that P divides order of G by N of A. Fine. This is what we are getting. So we are getting P divides order of G mod Na. Now we are using this thing in this this fact. This can be written in the form P divides order of G divided by order of Na. This is what we are getting. This can be written in this form. So this divides, P divides this. Now we are going to class equations. Class equation says that this portion is divisible by P. So this means this whole portion, sum is divisible by P. So this is what we are getting. On the other hand, order of G is divisible by P. So we are just transferring this to this side. So we are getting order of ZG. So we are writing it again. Let me write this. Now this says that P divides summation A don't belongs to ZG, because this is holding for all. So this is holding for summation A don't belong to ZG also. Order of G divided by order of Na. So this is what we are getting. This one is P divides also. P divides order of G. P divides summation A don't belongs to ZG. Order of G by order of Na. This means from equation 1. Equation 1 says that order of G is equal to order of ZG plus summation A don't belongs to ZG, order of G, order of Na. And this is what we are getting. Now we are transferring this to this side. Keep this, transfer this side to this. So we are getting order of G minus summation A don't belongs to ZG, order of G by order of Na. Fine. And this is equal to order of ZG. Now P divides order of G. P divides summation this order of G by order of Ni, or P divides this, P divides this. This means that P divides this whole chunk, this whole group. Now P divides order of G, P divides summation A don't belongs to ZG, order of G, order of Na. This means P divides order of G minus summation A don't belongs to ZG, order of G by order of Na. This is what we are getting. So this means that from this equation, let it be equation 2. So therefore, from 2, P divides order of ZG. Now, G is a finite group with no proper subgroup, because we are taking the case where there is no proper subgroup. So this is the case of no proper subgroup. So this is actually the case when, sorry, G as a proper subgroup, right? No, there is no problem here. G as a proper subgroup. Okay. So that's a mistake. So let me check. Let me correct this. Let me correct this. There is little mistake here. Now P divides. Now P divides order of ZG. This means that order of ZG is equal to 1 or P. But order of ZG can't be equal to P. This is not identity. This implies order of ZG sorry, because this is not having a, it has a proper subgroup, right? So there is some doubt here. Let me check. So order of ZG is equal to 1 or P. So because we are taking the case this is not equal to this. This means that just a moment. Just a moment. Just 1 second. There is a little correction here. So we are getting, so we are not getting this because this is not the case here. We are doing this in different direction. Let us check. Now P divides order of ZG, right? Order of ZG. Now this is the case when P don't divides order of H for all proper subgroups of G. This is the case when P does not divides order of H for all proper subgroup. But here P divides order of ZG. This means that ZG is not proper subgroup of G. If this is not a proper subgroup of G, this means that ZG is either E or is equal to G. But ZG is not equal to E. So we are not taking it. This is not equal to E. This means that ZG is equal to G. So this is G. And this means that G is abelian. Abelian. G is abelian. So this means, so we are getting P divides order of G, and G is finite and abelian. So we are using the Cauchy theorem for, so by Cauchy's theorem for finite abelian group, there exists A belongs to G such that order of A is equal to P. So hence the result holds for, hence the result holds for P does not divide order of G. So therefore the result holds for both the cases, case 1 and case 2. This implies the result holds for all n. So this is what we proved, hence proved. This is what we proved. So actually what we proved. Let's analyze the result first. Again, analysis. Again, the same thing we are doing. Analysis. It says that P divides order of G. G is finite group. Then there exists A belongs to G such that order of A is equal to P. So we have proved prove this theorem. So this is the proof. The main sketch of the proof is sketch of the proof. Sketch is, first you have to take order of G is equal to n. Then as in n is equal to 1 case, then n is equal to greater than 1. Then you have to prove n is equal to 2. We will prove this theorem for n is equal to 2. Then there is induction hypothesis. Induction hypothesis for all groups of order less than n. Then we prove the result prove the result for n. So when we are taking order of n is G is equal to n, there are two cases. There are two cases. There are two cases in case 1 is no proper subgroup. No proper subgroup. There is no proper subgroup of G. And second case is there is proper subgroup of G. Then using this case, second subcase, that is P divides order of H. P don't divides order of H. So we are proving the result for these two cases, subcases, and this case. These are the two cases then, case, and these are, so let me write this properly. So we are writing this as this is a case, this is subcase. Fine. So this is the sketch of the proof. This is how we have to follow. In this case, we will use class equation. class equation. So this is what the proof of this theorem, that is Cauchy's theorem. Cauchy's theorem for finite groups. This is how we do this. Okay. So this completes the proof.